So when you're using these sum and difference properties, identities, especially with Radian Measure, it gets a little bit strange how to break these up. But help me out here. What are some Radian Measure? So like for degrees, you're supposed to know 0, 30, 45, 60, 90, right? And then of course it's all reference angles after that. It's reference angles. It's always been reference angles. All right. What about radians? 0, pi over 6, pi over 4, pi over 3 pi over 2. All right. Now notice something. What's the LCD of all this? Of all those radian measures?
12.
12. And look at all this. Look. 12.
12.
All right. I don't know if you guys are with me at all. So like, for example, what is pi over 2 minus pi over 3? That's not a very interesting one. Let me do pi over 2 minus pi over, that's not very interesting either. Let's do pi over 3 minus pi over 4. There we go, Jeff. Let's do that one. What's pi over 3 minus pi over 4?
Pi over 12.
Yeah, because you would do 4 times 4, you would do 3. So you get 4 pi minus 3 pi is pi. Is everybody with us? Pi over 12? So now do you see how pi over 3 minus pi over 4 is how you want to rewrite, for example, if I assign this one? Do you see that? All right. So your task is to figure out, and I really would like you to try to stay in radians. Your task is to figure out what two angles add or subtract to be this guy that are angles we know stuff about, right?
Thank you.
You're welcome. And one of the easiest ways to do it real quick is if I have 7 pi over 12, that's like pi over 12 plus 6 pi over 12. And hopefully you guys see how that's dumb because I don't know shit about pi over 12, right? So let me see. What's another way to do 7 pi over 12? I could do 2 pi over 12 plus 5 pi over 12, but then 5 pi over 12 sucks. Do you guys understand what I'm saying here? So maybe it's 3 pi over 12 plus 4 pi over 12. Now that looks encouraging because I know those. Yay! All right, so that's kind of a nice sort of systematic way you can try to figure out what are the two angles I want to add or subtract to make the inside so that I can use the identity on it. Is everybody with me? So it's really the exact same question we ask when we have to do cosine of 15, but cosine of 15 is stupid easy because I'm used to seeing degrees, and it's going to be 45 minus 30 like we did the other day, or even 60 minus 45, right? Maybe. All right. So perfect question that got me right into it. Anything else from homework stuff, guys? Anything, or general questions or practice quiz questions? You guys doing okay out there? You guys tired of me asking that? I'm sorry. In a classroom, I could just kind of look at everybody's face and go, well, he's not doing okay. She looks okay. She looks like she's doing horribly. He looks okay. So I don't have to ask as much. All right. We'll clear all this away. If there are no more questions, we're just going to get right back into where we left off. Okay. So I want to, all right. So now we're getting into the identities. I don't know if you guys have picked up on this, but do you guys think I like this stuff right now? Do you think I like this stuff? Anybody? Have you picked up on the fact? Yeah, I like this stuff. I'm weird. I like this stuff. So it's kind of weird for me to say I hate 9-4. I really hate those. They're barely ever used. But if I had to sit down and do it, yeah, I just give me the formula, no problem. I could do it. So, but I wanted to point out one thing. So yesterday we proved these, right? Was it yesterday? Well, these two, I'm sorry, we didn't prove this one. Right here. But let's see if we can prove this one. Yeah, let's do that right now. Neat. I wasn't even thinking about doing that, but we might as well. How the hell would I prove this knowing what we know up here? What is tangent of 2 theta? What is tangent of any angle equal to by fundamental definition? What over what? Tangent is what over what?
Y over X.
Okay. Now, in terms of sine, cosine, secant, cosecant, whatever.
Cotangent.
Did you say 1 over cotangent?
Yes.
Okay, so that's true, but that's not, but okay, that's true, but that doesn't have anything to do with these.
Sine over cosine.
Yeah, so tangent of 2 theta is sine 2 theta over cosine 2 theta. Yes? And don't I know those? So the top is easy. Sine 2 theta is always, can be written as this. What's wrong with the bottom? Of course, who's on the bottom? This jackass. And what's he do? Have fun. It's like, oh God, you jackass. I love this. But let me spare us. It's gonna be this guy. So let's see if I plug that guy in. What in the world? So remember, I'm trying to get here. What could I do? Do you guys see what I could do? I really. Look at the top. I'm supposed to get 2 tangent theta, correct? What do I currently have on the top that's good? I have a 2, and what else is good, and then what's missing? Or what's extra too? Yeah, I really want you guys with me. What is tangent? Again.
Sine over cosine.
Sine theta over cosine theta. So what's good? I have 2 sine theta, don't I? Don't I want 2 sine theta? Do I want this stupid cosine theta?
No.
No, in fact, I don't. Not only do I not want that cosine I have already, I actually want an over cosine, don't I? So if I divide top and bottom by cosine, I kill this guy, but do I get what I want? So I should actually not divide by cosine. I should divide by cosine. Yes.
Right.
By piece. No, by cosine squared. So if I divide by cosine squared, let me get rid of this stupid line. Stay with me now. Stay with me. You guys are like, I haven't been with you in a while. Let me just put this underneath each so it's easier. Do you guys see how that works? So now I kill this cosine, and now it's sine over cosine is tangent. And what happens here? This is 1, and this is tangent squared. Come in. And this tangent double angle is one of the formulas I am not making you memorize. Why? 2 reasons. I don't currently have it memorized, and it is something the department decided was unnecessary to memorize. So, cool. All right, but these guys you definitely have to have memorized. These guys. All right, now next thing I want to point out, let me clear this away. Go. In the process of figuring out the half angle formulas, let me see, I don't know if you guys are going to remember this. Oh, these are all examples. Look at all these examples you guys get. We actually got to this position right here. I don't know if you guys remember. So just to really quickly kind of show you this again. So remember, cosine 2 theta is 2 sine squared theta minus 1, right? Remember that? All right. So if I can solve for sine squared theta and I get here, and then the next thing we did was we square rooted both sides, correct? Remember that? That was on the way to the half angle formula. These, now why do you think they call these reduction formulas? What is true about each of the things on this side, on the left-hand side? What's true about them?
Squared.
They're squared. And then what's true about each of the trig functions on the right-hand side?
They're doubled.
All right, the inside is a double angle, but what power is on the cosine?
Oh, they're just by themselves. One.
Yes, so the first power. So these are actually, I normally see these called power reduction formulas, which actually makes a lot more sense than just reduction formulas. They're power reduction formulas. So if I'm given sine, I've got to figure out sine squared of something, I can rewrite it like this. So here, watch this. Let me see. Let me clear all this away. Clear. So if I was asked to figure out sine squared of 15 degrees, that would become 1 minus cosine of what? Over 2.
30.
30. Okay. Now, to be honest, the reason I very often forget these crazy ass things is because they're sort of like midpoints between one thing and the half angle formulas. So when are these useful? They're going to be crazy useful in calculus. But I don't know. I don't care much about them at the moment. If I'm in calculus, these are hugely important. If I'm in pre-calculus, they're important if the question asks me about it. Okay. Let me clear all that away. Are you guys semi with me? So it's just a recognition that every step we take when we modify an identity, when we do something, even a middle set might itself be a useful identity. So how many possible trig identities are there? An infinite number. Yeah, so thankfully we're not going to look at all of them. Well, let's see. Now this is interesting. All right, here's a little something that's semi-interesting to me. How would you do this? Cosine, let me write it up here. The fourth power cosine. How could I rewrite that to not have, to only be a first power? What the hell could I do? What is, so
After it,
how do you mean factor it? What do you mean?
like cosine squared x times.
Yes, exactly. And then I know what each of these are, right? I would write this twice. Now, all right, now, no, all right. Do it. I'll sit here and wait. Do you guys understand what's happening? So cosine to the fourth is cosine squared times cosine squared. And I know, oops, let me make this an x. I know what cosine squared is, so I can just write that twice. Let me show you a little cool thing. I could pull out 1/2 and 1/2 and make it 1/4. So then I'm only having to FOIL this out. Do you see what I'm saying? Just get the fractional part out of the way. Now, it's just a little bit cleaner, right? I can read your minds. You're all like, how many more weeks do we have? I understand. At the same time, I hope somebody out there's like, man, this shit's crazy, but some of this stuff is neat. Let me write this over here. So the reason that I really like this, do you guys see what's going to have to happen? So when you FOIL this bad boy out, 1 plus, and then I get cosine 2x and, oops, and another cosine 2x. So I get 2 cosine 2x. So far everything's great. Everything's great so far. And then I get freaking cosine squared 2x.
I have a question.
Yes.
Why it's 1/4? Is it
Because, sorry?
is any 1/2?
Definitely not. Because what's 2 times 2?
4.
Yeah, okay. So it's not, there's not a plus sign in the middle. I didn't factor a 1/2 out. I took a 1/4 out front.
Oh, I see. Yeah.
Now, is there something wrong with this in terms of what they want me to do? Yeah, this stupid thing. So what is cosine squared 2x? Yeah. What is it? Oh, isn't this fantastic? Aren't you guys loving this shit? It's almost like I'm trying to make you hate me. All right. Come on, you could do this. You know what cosine squared of any angle is? It's this. So what's cosine squared of 2x? 1 plus, you can do it, with a 2 on the bottom, cosine of what goes inside? Whatever the angle is, what do I put here?
2x.
Twice that. So what is the angle
Oh.
right now?
It'd be 4x then.
Good. It'd be 4x. I like it. So this is a thing about identities are rules. They're rules that help you rewrite something in terms of something else, right? Sort of like this is one of the most fundamental identities. This is an identity because it doesn't only work for certain values of x. It's just true, and it's a demonstration of the distributive property, right? So stay with me now. Stay with me. Identities are rules. They're demonstrations of how to transfer something into another form. You have to really understand what it takes to make it happen. So no matter what the thing I have right now, I know what's supposed to go in its transformed state. I don't know if this is making any sense. Remember when I was like, okay, sine 2 theta is 2 sine theta cosine theta, yes? Sine 4 theta is not 4 sine theta. So this is basically the same kind of thing I'm talking about right now. That's no good. That's bullshit. That's a misunderstanding of what the identity is trying to tell you. So identity is trying to tell you if I have sine of twice something, that something goes here and here. So this should have been twice 2 theta, of course. We talked about that before. Okay. Okay. I know this is weird. I know it is. Okay, let me clear all this away. Clear it away. Here we go. Go away. Clear. All right. Blah, blah, blah. Now look at this crazy ass thing. So up here we had cosine to the 4th x. So what do I do with sine cubed? I can do the same thing we just did. Oops, somebody's chatting at me. Oh, I'm sorry. I'm gonna miss everybody's chat because Zoom updated and screwed me over. I don't know when anybody's chatting at me anymore. So just to cut to the chase, if I have sine cubed, I can write that as sine times sine squared, of course, right? And do you see how there's a sine 2x in the answer? So it tells me I'm on the right track, right? And of course, this piece, I just have to use the thing that's off the screen now, right? The sine squared version of that. Oh, by the way, let me clear this away. Well, yeah, I'll talk about this in a minute when we get to the half angle stuff. All right. Let me clear that away. All right, where are you at? Here's the half angle stuff. Let me point something out. All right. So look, here's another example of cosine being an asshole. You ready? Because these are the ones you have to memorize. Oops, not the tangent, sorry. These are the ones you have to memorize. No, not the tangent, Jeff, sorry. Look what cosine does. Here's sine. Oh, come on, here we go, sine. And then cosine's like, oh, I hate it. Right? Doesn't like. And then here's cosine. Cosine's like, oh, okay, I'm cool because I'm with myself. Ha ha. Anyway, I'm sorry. That might be a little bit of a reach, but they're basically the same formula. Do you guys see that? They're basically the same formula. The only difference is right there. That's it. So I'm trying to give you ways to help you memorize these things. And this is one you have to have memorized. All right. Let me clear this. Oh, yeah. And we already did a problem like this. Remember, we did that already. All right. I think that was it for this section. Yes, that's it for this section. I like it. The next section is just, anyway, I don't want to make it sound that horrible. These are so used in very strange places. When they come up, you dredge this up and you go, oh, okay, I can use this now. I am not going to go through the derivation. I just am not. There they are. There's the derivation of how you get here. So this is obviously called product to sum because it starts with the product of two trig and it makes it into a sum of two trig. So that's a continuation of the creativity of math people. What does it do? It's product, sum, we'll call it product to sum. So we're not the best at naming things. So, and then we have the other way around, sum to product. And this is where things get really kind of nifty. So these, again, none of these are any that you have to memorize. I definitely do not have these memorized. Have I ever used these in my math courses? Definitely. Often? No. When I need them, I look them up and I use them. So that's fine. The other ones that I'm making you memorize happen so frequently that it is more important to have those memorized. All right. Blah, 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 blah. So I really want you to understand. I really hope you can work through the fact that I am not myself very impressed by this. It still is useful. It still has its uses. It still is interesting, but it's just not as interesting. So when you do the homework, are you going to be like, well, he doesn't even like these. Why should I have to do them? Because I could do all this homework, even if I hate this stuff, I could just throw numbers in and do shit. That's all I'm going to ask you to do in the homework. You're going to have these sitting next to you. You just throw stuff in and you do shit. Right? So it's really, that's all it's going to be. Okay. Blah, 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 blah. All right. So the main thing I want to talk about tonight, now that I've blasted through all that, is how to solve trig equations, real trig equations, right? And let me not show too much here. All right, so let's attack. Let me turn off the Death Star back here. Strangers in the night. There we go. Okay. So let's do this. Let's start with a very simple example and then ramp it up, as we often do. All right. Is that too close? No. Let me get rid of we're doing some hypothesis testing in the stats class. All right, let's start with a really nice one. Let's see if you guys understand. Well, let's see. There's a twist to this stuff. Yeah, sure. We'll start with that. All right, so how to solve this equation. So it definitely is not. All right, real quick, a little side note. If I said solve sine x equals 0.913, then you're allowed to use inverse sine and do some shit, right? You understand what I'm saying? This should be obvious that I don't want to see no inverse sine, right? Ignore my poor grammar. We'll actually come back to this in a minute because it's not as easy as it seems at first, and it's a different kind of thing. Stay with me. So can somebody tell me what the basic, well, let me see. I don't know how to say this.
Pi over 6.
Okay. That's part of it. Why is that not the complete answer?
Because there are like infinite many.
I really want how many are, let me see. All right, watch this. So one answer is pi over 6. Now, here's pi over 6. What's another answer?
5 pi over 6.
Yes, because that would be a reference angle of pi over 6. All right, now listen. And then aren't all of the infinite answers, let me turn you down. Aren't all of the infinite answers related to those two, right? Stay. You're gonna fall over? You gonna be all right? Good. Let me try this again. Aren't all of the infinite answers related to those two? What do I mean? Like, aren't there infinite answers that are related to just turning here, even going backwards here? Yes? Yes? Because that would be coterminal angles. They would have the same trig values, right? Is there a way? All right, let me draw this again. So I can say, let me see if you guys are cool with this. What is that equivalent to? Let's just focus on this guy first. If I rotate around, what am I adding on top of this?
2 pi.
2 pi. And how many times can I do that? Get another valid answer. Like Jordan said, infinite number of times. So we use the letter K. Now, something I disagree with the book about, and I think I'm gonna just write it like the book does, just so it's not too weird. We use K. Now, stay with me. We use K as a variable that represents an integer. All right. So N normally represents 0, not 0. Represents 1, 2, 3, blah blah blah. K represents negative, blah blah blah, -3, -2, -1, 0, 1, 2, blah blah blah. You guys still with me? All right. So there's no reason for me to put plus or minus because K could be negative. But the book puts plus or minus. So, okay. And you're all like, really? That deserved that long of a, yes, it did. I'm sorry. Now, can I do something similar for this guy? Yeah, I could do something very similar for this guy, correct? It hurts me to write this. I'll be all right. Is everybody with me? Anybody not understanding what's happening? So all this does is it captures all the infinite other answers. And do you guys understand it's kind of silly? They're not really other answers in a sense because they're just coming back to the same place. But they actually are other answers. But later in math, you'll see how that looks. Now, is there a way to write this in one statement? Do I need 2 statements? And I'll just tell you the answer. Yes, you do need 2 statements because you can't go from here and get this guy and then see how it's a different distance that you would go. So you can't do it in one statement. Just stay with me. I love you guys. We'll do an immediate example where you can do it in one statement so you can see what I'm talking about. Here we go. We'll do an example. All right, somebody cool with this. That's the answer. That's it. That's all the solutions to this. Now, how about this?
3 pi over 4.
All right, so we got 3 pi over 4. And of course, we can do the same thing as before, right? Cool, is that right? All right, now what else?
Seven pi over 4.
Yes, right? So it's got to be where sine and cosine are different signs, of course, so that it comes out negative. Is that cool? And of course, it's got to be 45-degree angle because that's where sine and cosine are equal. And that's why tangent would be 1. Okay, I like it. So it's got to be this guy and it's got to be this guy. Now, you should automatically notice something here that gives it away, that I don't have to have two separate things. Plus, well, you'll see in a minute. So instead of starting at this guy and going all the way around, can't they go, how far is this?
Just 1 pi.
Good. And then how far is this?
The same again.
A pi. So I can consolidate this bullshit. I can say, let me use a better marker. And I really want you to understand that the answer we get is going to make all the sense in the world, because I can pick up the other answer and then come back and pick up the next answer for this guy using one thing here, which will be pi k. Get in there. Not par k. Par k. All right. Why does this make sense? What's the period of tangent?
Hi.
Yeah, okay. And what's the period of sine and cosine? Is 2 pi. So the other one we did was a sine at 2 pi. This is tangent, should have pi in it. That should make sense. Kick ass. All right, all right. Okay. So what about, oh, let's see. Yeah, let's do that. Yeah. This one's definitely neat. So real quick, how would you solve x squared equals 1/2? What would you do?
Square root both sides.
Square root.
Plus or minus.
Yes, plus or minus. X equals plus or minus rad 2 over 2. So equals 1 over rad 2. Got to multiply by rad 2. Okay. So basically, we do the same thing here, don't we? Square root plus or minus sine x equals plus or minus rad 2 over 2. So far, so good? All right, finish it up. I'm tired. Remember earlier when we did the sine equals, was it? No, we did cosine equals 1/2. Was that what it was? No, sine equals 1/2. And it could only live in the upper hemisphere. It could only live in the where y was positive. Well, what quadrant are the answers going to live in for this equation?
All of them.
All of them. Because sine can be positive or negative. That's all the frickin' quadrants, right? Frickin'.
So is it just pi over 4 plus all of them?
Plus all of them, I like it. So one answer is pi over 4 for sure. And then another answer would be 3 pi over 4, and then 5 pi over 4, and then 7 pi over 4. Are all of these separated by the same angle?
Yeah.
Yeah. What angle are they separated by?
1/2
Pi over
pi.
2.
Yeah.
Pi over 2. I love it. You both said the same thing, but different. I like it. All right, let me make sure you guys are with me. So the main ones I get are these. Do I have to write 4 different frickin' things? No, I don't. because I can capture all of them starting from him and going a multiple of pi over 2 around and around and around and backwards and forwards and whatever. So that's why I like you draw a little picture for yourself, and that will help you figure out what's the best way to put the answer. So now I can go plus or minus what?
Pi over 2.
No, I mean, let's keep going.
2 pi. Okay.
Pi over 2. Okay.
Oh, yeah.
Maybe. Definitely. Okay, all right. I like it. All right. So what about this? All right. Has everybody got that down? All right. You should expect what's about to happen. All right.
I have a quick question.
What's up? Hopefully it wasn't.
Oh no, so I know you put x equals pi over 4 plus or minus pi over 2, okay? So after the plus and plus minus, is it just a period times k?
Well, again, but is this period of sine pi over 2? No. So why was it that I picked pi over 2? Because that is the distance between each of these. So I'm going to rotate this amount this many times to get to whatever answer I want. Because if I rotate by pi over 2 that way or that way, so many times I keep bouncing between the answers. I really want this to make sense. But if, like, the first answer we got was this, wasn't it? If I go this distance and then I go that same distance again, do I get to another answer? No. So I couldn't do it like so compactly. We had to have two separate statements, one for this guy and one for this guy, because I couldn't capture the answers by going the same step size. There wasn't another one down here. Damn it. Right? Okay. But here, a step, a step, a step, a step. I caught them all. I just need one line with that step size here. Okay. So it's not really period, it's distance between the answers. And if the distance between all the answers is the same, I can capture it in one fell swoop.
Okay, that makes more sense.
Like it. So let me do a different one than I was about to do, just to really hammer this home. Yeah, let's do this one. Let's see. Can I put this together? Yes, I can. I can do it. That's it. Have faith, Jeff. You could do it. You did it. Okay. So this one is somehow going to be different. So the first step is the same as it was a minute ago, right? You guys all with me out there? All right, so I'm going to take a square root, plus or minus. Do I get a value that looks familiar? What do I get?
Square root 3 over 2?
Yeah. Doesn't that scream at you? You know me. Mary, don't you know me? No, all right, sorry. So how many quadrants are the answers going to live in? All four. Yeah, of course, because it could be positive or negative. So that's all of them. What angle are we talking about fundamentally? What's the reference angle for this?
Pi over 3.
No. Pi over 6.
Pi over 6.
Closer to the x-axis. So this will be pi over 6. Then over here, I'm going to have 5 pi over 6. And then I'm going to have 7 pi over 6. Get in there. And then I'm going to have, what's this going to be?
11 pi over 6.
Yes. 11 pi over 6, because this would be 12 pi over 6, right? All right, let me take them out of here so you don't think that's part of the answer. All right, now all four of these equidistant apart. What distance is this from here to here? How do you find the distance between two numbers? Subtract. So what
Pi.
distance? Yeah? 5 pi over 6 minus pi over 6? It's 4 pi over 6, 2 pi over 3. Is this the same distance?
No.
No, shit. So I can't, I'm gonna have to write more than one line, but aren't these, how far apart are these?
1 pi.
1 pi, how far apart are these?
The same. 1 pi.
1 pi. So I can write something based on pi over 6. If I go pi away, I get to the next thing. I really want you guys, this becomes kind of like a loop here, right? Pi over 6 is some pi over 6 some pi, pi over 6 some pi, pi over 6 some pi. This same thing here. This distance from here to here is the same as this distance from here to here. So I can capture all of those answers in one line. Get in there. So why is that not 2 pi? And that was because it's freaking squared. Shit gets weird when it's squared. There's no question. Okay. All right. Maybe. You knew these were going to be weird because there's an infinite number of possibilities. So thank God there's a more concise way to capture an infinite number of things, right? Let's go back to this dude. I'm going to erase all this. So you guys might think that's easy. I can use my calculator, yay, but it's actually worse. I'm going to erase this. Here it goes. So let me pull him over here. So somebody help me out. So what would this look like on paper to solve this? What would you do to both sides to solve it?
Take the inverse.
Take the inverse sign. So somebody help me out. What do you get when you throw out in the old calculator? In the old calculator. Curious what mode you guys gonna give me. Okay, I'm ready for either mode.
1.15 rad.
Okay, 1.15 rad. I'll take it. So that is, where is that? What is pi over 2, roughly? Pi is 3.14, so pi over 2 is 1.57. So 1.15 rad is in here. Is that cool? Where's there going to be another answer? So we're still going to have to do plus or minus something. Where will there be another answer? So, I mean, before when we had pi over 6 was an answer, what was the answer here? Wasn't it pi minus pi over 6? So it was 5 pi over 6. Are you guys with me? So, okay, same thing, same exact thing. So here's one answer. Isn't the other answer going to have the same reference? 1.55 rad. So what is the actual angle? Pi minus 1.15. Doing the old calculator. See, this is a complete calculator problem, but you got to know what to plug in the calculator. It's like 1.99 something.
Yeah, 1.991.
I almost picked something that made it 2. That would have been so cool. Too bad for everybody, Jeff. We'll just say 1.9. So I've got 1.15 rad, give or take 2 pi k, and I've got 1.99 rad, give or take 2 pi k, because I can't capture them going the same step size, right? Does that make... See how that's a little worse than you thought it would be? I mean, you're like, oh, I can plug in the calculator. Ah, shit, that's actually worse. All right. But it's not that worse. It's not any different than what we did before. It's just we're not used to doing this kind of thing. But it's the same thing we did before. It's the exact same thing. All right. Maybe. All right. All right, now I can finally do this one. Let me see, you guys ready? All right, here it goes. Going away.
Wait.
You had chats yelling at you too.
Oh, geez, I can't. Yeah. Wow, as a kid, we didn't have smartphones. You think I'm going to be good with this chat shit? All right, here we go. Everybody ready? Okay, one person's good. All right, let's see what happens.
Yes, thank you.
Sure. All right, I guess I can kill you off too. We did you. Ha, go away. All right. I really should have been coming up with a good problem. It's too bad. So let's do this. Yeah, okay. So I got 2 sine squared x. Wait, let me think. Yeah, sine squared x. Plus sine x minus 1 equals 0. It should be really, really kind of obvious what you're expected to do here. Or is it? I don't know. Maybe it isn't. Hello?
Factor?
Yes. So one thing, if you want to, you can replace this with U if you want to, or S. I'm going to do U because my S's look like 5s. And then you can factor it. What do you get when you factor it? So you get 2 minus 1 is positive U. So that means that 2U minus 1 equals 0, or U plus 1 equals 0. So U is 1/2, or U is -1. Don't circle this shit, because the question don't care about U. Aw, I'm sorry, everybody. But you knew that. You knew the problem didn't care about you. So I got to get it back in terms of the variable it wants, which is x. So this is sine x equals 1/2, or sine x equals -1. All right, finish it up. Solve. I think this is the first one we did, right? So you could just copy that down from your earlier notes. So we did this earlier. We got pi over 6 plus or minus 2 pi k, and 5 pi over 6 plus or minus 2 pi k. What do you get for this guy? I can only go so far. Oh, all right.
Pi?
No, you're thinking cosine.
Oh, pi or 3 pi.
Yeah, 3 pi over 2, and then of course you pluck on there plus or minus 2 pi k. Shapow.
So then do you want us to use the book's way plus or minus, or do we just use K?
Well, doesn't the book use k? Let me see. I think they use k, but they use plus or minus, don't they? Let me see if I should really not just trust my memory. Let's see. Yeah, they start off with just 0 to 2 pi, which is boring. Get out of here. Barfity barf barf. All right, where do they do the dad gummit book? Give me a good problem here. There it is. Yeah, this is basically the way they do it. Plus or minus 2 pi k. Yeah. So in the future, you might be in another class with another teacher with another book, and you don't need the plus or minus because k can be negative. Is it really that big of a deal? Not really, but it's just kind of like annoying to me that this book does it, but it's a free book. What the hell do I want? Okay, let's do one last problem, I think. Yeah, let's get out of here early tonight. Let's do one last problem. How's everybody doing? Let me keep an eye on things. All right, I think I've been talking about other stuff long enough. All right, so let me see if I can freak you the shit out. You ready? What about take on me. All right. All right, now what are you guys concerned about as you look at this?
3.
Yes, that's a good thing to be concerned about. What I want you to realize is, all right, so remember the very first thing we solved was did I use a theta or it doesn't matter, Jeff. Sine x equals 1/2, right? Isn't that the very first thing we solved? Would there be a different answer if it was sine theta equals 1/2? Would that have been a different answer? No. What if it was sine of a equals 1/2? Would that have been a different answer? No. Okay, so the first step on this problem is to treat 3x as an angle. It's the angle 3x. Just like theta, just like x. So therefore, this is easy to begin with. What's 3x equal to then? What are the two possibilities? Where am I?
Pi over 3. Oh, negative. The other one.
I have a 3 reference angle, so I'm going to be
2 pi over 3.
no, because that's still where sine is positive. It's going to be down.
Oh, JK, it's 3 and 4.
Yeah, so I'm going to be pi over 3 past pi, which is 4 pi over 3. Is that cool? And of course, what's this one?
5 pi over
Good,
5 pi over 3.
Plus or minus, right? Plus or minus what? This is not a nice situation. I have to do this turn, and I have to do this turn, right? So I've got to do a full turn and a full turn. Everybody with me so far? Now we go, oh shit, wait a minute. That's a 3. That's not a 3x like an angle. So the last thing I do is divide the stupid 3 away. See how much better that was than it felt like it was going to be? So now all I do, now here's what I got to get, this isn't that weird. I'm going to divide by 3, 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 divide by 3. So I get now my two answers are 4 pi over 9, give or take, 2 pi k over 3, or 5 pi over 9, give or take, 2 pi k over 3. Now where things get weird is if they ask you to list all, if I had to list all the answers from 0 to 2 pi, if I had to answer, I guess they do this, from 0 to 2 pi, I have to do every value of k for this and every value k for this until I get up to 2 pi. So what do I mean? So if I had to be between 0 and 2 pi, this would be 4 pi over 9. Let me just go ahead and do this. Do you see how this is going to be 6/9, right? So then 10 pi over 9, is that still in here? Is 10 pi over 9 still in there? Yeah, it's just a little over pi. Is that cool? You guys with me? So then I got to do another 6 pi over 9 plus this is 16 pi over 9. Okay, where am I still in here? Yes, and real quick, what is 2 pi? What is that over 9?
18.
18. So then I know where I'm going to stop. So wouldn't I stop right there? Because the next one would take me over this. Yes? I have no idea if you guys are with me. Because sometimes a lot of these problems are going to say, find all the answers inside here. Well, I always do this, period. And then I can go, oh, you want it in there? Okay, I'll just get all the ones. I just make them, right? So here I do the same thing. 5 pi over 9. Add 6 pi over 9. Add 6 pi over 9. And then I know I'm done. Because the next one would go over that. So that's not too horrible. It's my hope, right? If there's anyone out there who never sat down and memorized their angles, you're going to continue to hate life. If you did memorize your angles when I told you you should, this shouldn't be that horrible. It should be kind of quick. It shouldn't be that bad. That's what I hope. And draw pictures for yourself. It's not a bad idea. It's a smart thing to do. Okay, I think that's enough. That's enough for me. That's all that matters. Let me know if you need to hang out. Otherwise, you're free to go. And I think the quiz should be open. Yeah, it should be open now. So if you wanted to start the quiz now, you could. Get it done and over with. Up to you. All right. So let me know if you need to hang out. Otherwise, I'll see y'all tomorrow. Peace.
Have a good one.
You too.
I need to hang out still.
Okay.
I cannot for the life of me solve 21. I'm still stuck on it.
All right. Here we go. Let's do this.
I'm getting frustrated.
9-1, 9-2?
9-1.
9-1. Okay. Oh, I just did. All right. Let's see. All right. So you catch me up here. What have you got so far?
Okay, so with 1 over cosine x plus 1 over sine x, and then I foiled it with the sine x plus cosine x. So I got sine x over cosine x plus cosine x over cosine x plus sine x over sine x plus cosine x over sine x.
Did you see what I did as you said that, right? Did you do this next? Because sine x over cosine x is tangent. Cosine x over sine x is cotangent, right?
No, I didn't do that. What I did instead was because I noticed like
Well,
it
now
was-
stop, because look at this. Remember this other piece?
yeah.
So that dies.
Uh-huh.
Dies. Done.
Oh my God.
Yeah. So you got to pay attention to everything so that you know. This sort of like what happened the other day. We had like a sine squared and there was something else, and I said don't distribute it because the bottom became sine squared. So it's like if you pay attention to other parts, you can see, okay, I don't want to do shit with this because it's going to die with this other piece, or right? Does that make sense?
Yeah, I can't believe we didn't see that. Okay.
No, it's you get hung up on a piece and you don't see the other piece and realize, why would I be hung up on something that wants to die, right? I understand, trust me. So it's just this idea of don't get hung up on a small part, keep everything in frame, because maybe that part you're hung up on is going to cancel, or maybe it's supposed to be there, or I don't know, right?
Okay, because what I started doing was, well, because I kept the sine x over the cosine x, and then I noticed that because both of them were like cosine x on the denominator, I did like sine x plus cosine x over cosine x, and then after that,
No, but this should be cosine over sine, right?
yeah.
So you don't have, and this will be sine over cosine, so nobody has a shared denominator.
Okay, yeah, that makes sense. Okay, thank you. I can't believe it was that simple. Okay,
No worries.
thank you, Professor.
Sure. How's everybody else? Are you guys actually out there, or are these my people that log in and leave? All right, maybe so. All right, I'm out of here.